Thank you for the kind invitation, and yes, thank you for giving me this kind of challenging task to do here. I'm supposed to give a short review on direct detection, and I should tell you about the XENON1T access that we recently published. So it's basically 2 talks, and I'm supposed to give all that in 25 minutes. So it's kind of challenging, and I will do my best. So to get started, by the way, can you see my mouse?
Yes, we can see.
Okay, very good. So to get started, we are here somewhere in our Milky Way, and of course you learned all yesterday, and you knew before that we are moving through the dark matter halo. For the purpose of that talk, we assume that the dark matter halo, though the dark matter, is made out of WIMPs, weakly interacting massive particles, because that is the prime goal for direct detection experiment. We also learned yesterday that there are kind of some uncertainties how this dark matter halo actually looks like. For that talk, we assume that it's a simple spherical standard halo model. So basically, it's a spherical halo with a 1/r² density profile. If we move through this dark matter halo, and one thing that we know for sure about the dark matter halo, it's not co-rotating. There will be a WIMP wind basically facing us, and if we place nuclei, that is our detector, in the lab, there will be WIMPs hitting the dark matter target occasionally, assuming that there is some kind of interaction between the dark matter particle and the ordinary matter. The typical velocity in that problem is the rotation speed of the sun around the galactic center. That's 230 kilometers per second. And even though that is rather large, this is small compared to the speed of light. So whatever we do here, all the calculations is highly non-relativistic. The signal we look for are nuclear recoils. So basically, it's really like pool billiard. The WIMP scatters off the nucleus suddenly gets a recoil, and this recoil is very small but detectable. If you look at the recoil spectra, so basically the event rate versus the recoil energy, you see this is not like a smoking gun signature from X to gamma gamma. So there's no peak. So what you expect is a featureless falling exponential spectrum, which already tells you that if you want to have a high sensitivity to search for these interactions, you better have a very low threshold, because the spectra are exponentially rising, and due to coherence effect, it is also favorable to have a heavy target like xenon or germanium, because we benefit from this A² enhancement. So to sum that up, the rates we are looking for, they're really, really tiny. We're talking about events per ton year in keV, a fraction of events per ton year in keV. We have tiny recoil energies. We talk about 10, 20 keV. Now, what we call KVR or KV nuclear recoil is already, you have to take into account that this is a nuclear recoil scale, so you have to take into account quenching effects. So the observable signal, number of photons, the number of ions, or so electrons, is even smaller than for an electronic recoil. Electronic recoils you would get from, for example, beta and gamma radiation interacting with the atomic electrons of the atom. The other thing is, if you want to search for low mass WIMPs, so this is a typical different WIMP masses, 5 GeV to 50 GeV, you see that the spectrum gets steeper and steeper. And if you don't have a low threshold, the exponential recoil spectrum will not make it at all over your threshold, so you will not see anything. So what is the experimental strategy for direct WIMP searches? At the end, it's summarized in that Feynman graph again. You have the target sitting in your lab, and particle scattering off this target. We search for low energetic nuclear recoil signal. Nuclear recoil is the signal. We aim for zero background in the search region. So it's all low background experiments that are optimized for zero background. But of course, please make sure we switched to flexible profile likelihood analysis years ago. So we don't have hard borders anymore. So usually we don't have a box anymore, and then we can really say in that box we have zero background or 0.01. So we put the background model into the profile likelihood analysis, which then optimizes the sensitivity. We want the lowest possible threshold, and we want the largest possible exposure, because you know so far we haven't seen anything. So to be sensitive, you need a high exposure. So what is the current status of the field? There's many experiments out there, and what is shown here are the results for spin-independent WIMP nucleon interactions. So on that axis, we have the cross-section or interaction probability, and this graph covers more than 14 orders of magnitude. And here we have the unknown WIMP mass. Both of these parameters are unknown. Even the interaction is unknown at the end. And this covers more than 5 orders of magnitude. And you see, you can easily extend this to 10 TeV and so on, but you just need a ruler and follow that line. What you see here is the depletion of dark matter in the halo. So basically, we have a known, or we assume that we know the local density quite well. And that means the heavier the WIMP particle gets, the fewer scattering partners are available. And that's why all the limits go up here. The limits are weaker on that side because of threshold. So if you don't have a threshold to be accessible, to have access to low mass WIMPs, because the spectra don't make it over your threshold, you will not see that. And that's why all the experimental results go up here. We will go through this plot in detail in a few minutes. There's one thing, they're all limits. Beside these 2 islands from the DAMA experiment, I want to quickly explain you what that is. The DAMA experiment takes a different signature, or search for a different signature, and this is the so-called annual modulation signature. So if the sun moves around the galactic center on its orbit, the typical velocity is, as I said, 230 kilometers a second. But now the Earth and the detector, our detectors are installed on Earth, is orbiting around the sun. And so you have to add or subtract the velocity of the sun to that orbital velocity, of the Earth to the orbital velocity of the sun. So in summer, the velocity is a little bit higher, so the spectrum is a little bit harder. In winter, you have to subtract the velocity, and the recoil spectrum that you expect is a little bit shallower. So that means if you have a certain threshold, but the spectrum changes, you will see a modulating number of events that makes it above the threshold or below. Of course, the majority of the expected signal given the standard halo model is an unmodulated WIMP signal. So you have a tiny modulation from this, it's a kind of a 5% effect on your signal above an unmodulated WIMP signal plus a background. So this is the signature that you try to find here, and the DAMA experiment claims to have seen this kind of signature since about 20 years now with a very high significance. So the significance is almost 13 sigma. Recently, they published data from their phase 2 with new data where they managed to decrease their threshold to 1 kV. So the modulation that they see, that's the modulation amplitude. It's only the modulating part is in between the 1 and 6 kV energy scale. kV here, important is electron recoils. They cannot distinguish between nuclear recoils and electron recoils, so they consider everything with the same energy scale. Now, the problem is, of course, that if you look at that plot, DAMA is excluded by many orders of magnitude by much more sensitive experiments. If you assume that the signal that they see is due to spin-independent WIMP nuclear interactions. But there are also other tests and challenges to the DAMA signal. So there are several experiments that basically try to test DAMA with the same principle. Sodium iodine crystals. So sodium iodine crystal read out by photomultipliers, and results by cosine 100 and nice. Cosine 100, this is this line shown here, excludes DAMA if you interpret it within that frame. The modulation analysis, really looking for this modulation, is still inconclusive, but Analysis did the analysis, and their data is consistent with no modulation and incompatible with DAMA at the 2.6 sigma level. More data is needed to really clarify that, and there are even more experiments that are under preparation. If you make more assumptions basically on the interaction, on the model, then also the other experiments obviously exclude DAMA by a lot. So what are all these experiments? There are several technologies out there. DAMA is basically this kind of principle. You have a crystal, sodium iodine read out by PMTs. You can replace that principle by putting an ionization detector here, for example, a germanium detector. Then you would have a crystal target and read out ionization and not light, but it's the same principle. Then you have more complex detector concepts, which I will briefly sketch in the following. All these detectors, they suffer from background. So I already said we have low background experiments. So where are these background sources? If you have smaller detectors, we all go underground. We all employ some kind of shielding, and the typical background sources that are left for smaller detector are muon-induced neutrons. So basically, you have hadronic showers induced by the muons. They produce neutrons, and the neutrons, they of course are neutral and also scatter off the nucleus. So they produce a signature that looks like a WIMP. The difference is that a neutron has a rather high cross section. It can scatter several times in your detector, while a WIMP will never do that. Electronic recoils, beta gammas, they will always interact with the electrons because they are charged and produce electronic recoils. The typical sources for that are the detector itself. So natural gamma radiation, neutrons from alpha N and spontaneous fission reaction from the detector construction materials or from the target itself. So if you have activated or active isotopes in your target itself, from activation, from impurities, and so on, obviously this will contribute to your background. If you now go to ton scale detectors, typically the natural gamma background of your detector does not matter anymore because you employ self-shielding. If you have a ton scale detector, you can sacrifice a little bit of the side of your detector. You don't use that for your analysis. Typically also muon-induced neutrons are not relevant anymore. What becomes relevant are impurities like 2 neutrino double beta decay isotopes and of course neutrinos. Low energetic solar neutrinos, they will scatter off the electrons, produce electronic recoil signatures, and high energetic neutrinos, boron 8 neutrinos, atmospheric neutrinos, they scatter off the nucleus and provide a nuclear recoil signature that at the end, due to the small cross-section of the neutrino, is basically an irreducible background. It looks like a liquid touch. So I hope I could show you that many of these signatures are basically electronic recoils. So all good experiments, all competitive experiments, they have active electron recoil background rejection, where we try to employ different energy loss mechanisms for nuclear recoils, so signals and electronic recoils background. For example, you see here in cryogenic volometers, here are the electron recoils, here are the nuclear recoils. So for the analysis, you will use that region. For liquid xenon, liquid argon Tpcs, you employ the charge to light ratios. You plot here the ratio of a light to a charge signal versus energy. And you see here's the electron recoil population, here the nuclear recoil population. What you see that there are some experiments or some technologies where these bands are very well separated. So you get a very high rejection factors at 100% nuclear recoil acceptance. Very often that comes as a price. For example, liquid argon pulse shape discrimination. You need to scan or to check the pulse shape of the scintillation light. Obviously, you cannot do that with 2 photoelectrons. You need quite some statistics. So the price is a rather high threshold. What you get is extremely good discrimination. Here, in this kind of detectors, that works down to really, really low thresholds, but you only get a mediocre rejection factor, and you have to pay a price. You lose 50% of your nuclear recoils. But this is all factored in your sensitivities. If you now go to back to that plot again, cryogenic volometers, these are basically experiments that are cooled down to millikelvin temperatures. What you measure is the temperature increase of your volometer after a particle interaction. And at the same time, the CREST experiment is measuring scintillation light from that crystal, or the CDMS and Edelweiss experiments, they're measuring charge germanium detectors. And then you combine these 2 quantities to basically exploit that here to discriminate electronic recoils from nuclear recoils. If you look at the results, they are dominating the parameter space at low WIMP masses because for these detectors, it's very hard to get a high exposure, but they manage to go to really, really, really low thresholds, 30 electron volts, 70 electrons, 60 electron volts. And that's why they are leading here at very low WIMP masses. If you look at this experiment, the Cdx experiment, this is a classical p-type point contact germanium detector, so operated at normal cryogenic temperatures, liquid nitrogen temperature. They managed to have the leading limit down to really, really low masses. This is just 50 MeV, dark matter masses. They managed to do that with this rather high threshold compared to the others by employing the so-called Migdal effect. All the results here with an M use the Migdal effect. We will have a talk about that just afterwards. So what is the Migdal effect? The Migdal effect is a hypothetical process that follows a nuclear recoil. So basically you have a WIMP scattering of the nucleus, and if the nucleus starts to move, but the electrons don't follow that movement instantaneously, it is possible that you kind of ionize the target in that way. And that means that the original nuclear recoil signal will give rise to Auger electron X-rays Bremsstrahlung, and this is something that is an electronic recoil. And the detectors are more sensitive to see electronic recoils. So by exploiting that effect that was not yet seen in calibration data, so it's a still hypothetical effect, you can basically make overcome this very steeply, sharply falling spectra, exponential spectra, because they extend to higher energies. And this is exploited here. Other experiments that are used are so-called single-phase noble liquid detectors. So you have a sphere that you fill either with liquid argon or liquid xenon. They're both excellent scintillators. And because it's noble liquids, you cool them down, you can realize rather large target masses. If you look at the target masses here, 830 kilogram X mass using xenon, deep 3600 is the largest currently operating detector with almost more than 3 tons of liquid argon. The problem is, despite these very large masses, both projects don't have leading sensitivities. Usually backgrounds is an issue here. And this led to some consolidation of the fields of deep joint dark side and X mass joint the xenon collaboration. Dark side and xenon, they're operating dual phase TPCs. So what are dual phase TPCs? Again, it's using xenon argon as an excellent scintillator, but they can also be ionized easily. So you operate these detectors as a time projection chamber. At the end, it's a cylindrical volume. The cylindrical volume is viewed by photosensors above and below the target. And this is one signal, is just a classical scintillation signal. So it's a light pulse. Now you operate as a TPC. That means there's a voltage across the target. The target gets ionized, the electrons drift upwards and then are extracted in the gas phase above the liquid phase, where they produce a proportional secondary light signal. So this is a light signal that comes delayed, which is directly proportional to the charge. So you have a light measurement and a charge measurement. Now you can use that, the information from the TPC to basically identify dark matter WIMPs. So that's nuclear recoils, background signals, betas and gamma. They will have a higher S2 signal with respect to the S1. If you have multiply scattering particles, then you have several S2 speeds, so you can use that to really lower your background. At the same time, you get target fiducialization. You can reconstruct the position, take only the inner part of the detector for your analysis and reject background. What you can do now to lower the threshold is you give up the requirement of a light detection. You only look at the charge. The price you pay is background and signal looks the same. You just have a charge signal. You have a limited fiducialization because you only have a two-dimensional position reconstruction, so you cannot fiducialize in Z, but the price you get is what you get is reduced thresholds. And this is shown here. At the moment, liquid noble detectors, most notably the XENON1T experiment, is basically dominating the entire field, starting from 180 MeV down here up to several TeV. The experiment shown here is XENON1T with a Migdal effect. This is a charge-only analysis. This is the standard S1, S2 analysis. Dark side 50 is a 50 kilogram liquid argon detectors up here. This is the charge-only analysis from dark side. And Panda X2 and Lux are two half-ton scale xenon detectors that have limits down here. So what are upcoming projects? If we go to the projections plot, then we see that the goal is, of course, to reach down to this line of the neutrino floor that I will mention in a second. The cryogenic volometers, they focus on lowest thresholds to really explore this low mass WIMP region here, while the liquid xenon, liquid argon TPCs, they will go for the multi-ton scale, so 5 tons, 6 tons. The projects down here is 20 tons or even 40 tons or even 300 tons, and lowest backgrounds. So what is this limit down here, this neutrino floor? This is from the coherent neutrino nuclear scattering. So boron 8 neutrinos here, atmospheric neutrinos here, produce this irreducible background signal. For example, what you see here is the boron 8 neutrino spectrum is identical to a WIMP of 6 GeV. They have exactly the same shape. So you cannot distinguish them anymore. And the goal is to reach down to that floor. The problem is it's not really a floor. So there's a well-defined definition behind that lines, but it does not mean that you suddenly hit a hard border and then you start to see a problem. So the first neutrinos you see in your background is basically an order of magnitude higher in the sensitivities. The exposures you need to reach that, we like to call it fork nowadays instead of floor, because you start seeing something slowly, and the deeper you go in, the more of these particles you see, is about 200 ton year exposure for liquid xenon and 1,000 ton years for liquid argon to reach down here. We are currently here, the best exposure is 1 ton year for liquid xenon. I have to speed up a little bit. So that's the summary of the first part. This is really exciting part times for direct detection, especially because we have many different projects coming online soon, and we have 3 multi-ton liquid xenon experiments that will get online soon. They are under construction or commissioning. And we have very good prospects to reach this neutrino floor in the next decade, especially here around the 6 GeV. We will start to see those boron 8 neutrinos very soon. So now let's come to the shorter and second part of the talk. Different hat on, that's the low energy electronic recoil signal at XENON1T. So XENON1T, I just showed you, dominates the entire WIMP direct detection parameter space at the moment. It's the largest liquid xenon TPC ever operated, about 1 meter and 1 meter in size, with a 2-ton active liquid xenon target. So far, we talked only about nuclear recoils. Nuclear recoils is down here. Electron recoil is the background, the dominating background in liquid xenon experiments. And the question is why it is interesting to look at these electronic recoils. Well, because there are many, many models that predict signatures from new physics in this low energetic electron recoil data. We choose to look for 3 different things, but there are many, many others. One is solar axion. So basically, if the axion exists, it should be produced in the sun. And because it's produced in the sun, it has keV energies. It has a funny kind of complex spectrum. Axion-like particles, bosonic axion-like particles, could be a dark matter candidate. They would lead to lines at their rest mass. And the third thing that we wanted to look into is enhanced neutrino magnetic moment. So neutrinos have an expected magnetic moment, which is extremely small, but beyond the standard model physics, could enhance that, and the cross-section would increase exponentially towards lower energies, depending on that neutrino magnetic moment. So it's basically a complex spectrum, an exponential falling spectrum, and this is a light spectrum, backed up by some theory. If you want to look for new physics in this low energy data, you first need to detect these kind of effects. Neutrinos, of course, is just elastic neutrino electron scattering. For axions and ALPS, you assume the axioelectric effect is basically an analogon to the photoelectric effect. You just replace the photon by an axion. And then you can write equations, and you can detect these kind of particles in liquid xenon detectors. What you see here is the solid line is production and detection. So production in the sun, for example, and detection in a liquid xenon detector. If you take reconstruction into account, energy resolution, detector efficiency, and so on, you get the solid curves, the solid regions. That is what you expect to see in our detector. The background model is rather complex. It has 10 components. It starts from liquid xenon intrinsic impurities. It's dominated by lead-214, which comes from radon-222 that's emanated from all detector surfaces. I just want to highlight one more thing. This is this 2 neutrino double electron capture signal that we published last year. We were on the cover of the Nature journal. This is the longest and isotope rare second order weak decay. It's the longest half-life ever measured directly. And for this kind of search, we need to take it into account in our background model. What else do we have in our background model? We have isotopes that are short-lived. They come from neutron activation, from calibration sources, but also from background. And we have detector materials and solar neutrinos in our background model. Now we take this 10-component background model and fit the data, and it agrees very, very nicely with our data. It's an unbinned profile likelihood fit. And the result in that region here is that we have a background level of 76 events per ton year in keV. This is the lowest background ever achieved in this energy range. But if you look very carefully, what you see here, at the lowest bins, there's an excess of events. This is important to note. The background model really takes into account this entire region here. It fits really everywhere besides at lowest energies. There's this excess in the 1 to 7 keV range. We observe 285 events. Well, we assume something like 230. So this is a simple, naive 3.3 sigma upward fluctuation. I have no time to go into details. All these events, they're uniformly distributed in space. They're uniformly distributed in time, as far we can tell. Again, it's an unbinned likelihood analysis. Don't look at that point. You choose the binning a little bit different, the point will shoot up again. So, but this excess persists, of course, also in the unbinned analysis. It's far away from typical background artifacts that we know, and we, of course, checked efficiency, reconstruction, and so on, all the way down to calibration. We have calibration sources where we basically can make sure that this is not a threshold effect. So what causes this excess? Well, many things. All the signal models we were wanted to check fit. Solar axions fit the excess of 3.4 sigma, neutrino magnetic moments, 3.2 sigma, bosonic axion-like particles. An axion like particle at 2.3 keV has a 4 sigma local, but it can have every mass of 3 sigma global sensitivity, and many other results, since we've made our result public, describe that model. Can we claim something? Well, the problem is the big but. Also, tritium describes the excess very, very well. We know that tritium is produced by cosmogenic activation. So if you place your xenon bottle above ground, there will be some tritium produced. But on the other hand, tritium is highly reactive. We also know how to get rid of tritium. So since we have to purify the entire xenon inventory, we are pretty sure that we cannot explain that excess. So we need only 3 tritium atoms per kilogram of xenon to explain that excess. A very small number, but we're pretty sure that it cannot come from xenon spallation above ground. But there are other effects. Maybe we have tritiated water, H2O, somewhere in our detector materials that are slowly outgassed. Or maybe we have tritiated hydrogen in our detector. We have no means to measure that. And if we would have 100 times more tritiated hydrogen than other molecules, which does not seem very likely, but we cannot measure it at the moment, it would be able to explain that excess. So the only thing we can say at the moment is, we can neither confirm nor exclude that tritium makes that excess. It's a valid hypothesis. So if you look at the summary, well, the excess is there. This is something that we are pretty sure about. It can be explained by many beyond the standard model things. It cannot be described by artifacts and can be described by tritium, but not by argon-37, which was also under discussion. So what do we do about that? Well, we are building a new detector, XENON1T. There will be a talk on that later in the session. And what is shown here is basically the question: assume that this excess would be from tritium. How much data is needed to distinguish it from solar axions from tritium? Well, and the difference is the spectral shape. And obviously, it depends on the background level that we will achieve in that detector, but basically in 1 year running time, at the background level that we target at, we should be able to distinguish the two hypotheses based on the spectral shape only, assuming that the signal persists at the more than the 8 sigma level. So we hope that we will be able to answer that question quite soon. So that brings me to the end of the talk. I just pop up that slide again. I think it's really exciting time for direct detection. There are many projects coming online now in the next years, and we hope to explore this entire parameter space. Sorry for going a little bit over time. But that's it. Thank you.